Rory here again. There are two key elements of power integrity analysis. The first is a decoupling strategy, which we'll do as early as possible to guide schematic capture. And then the second is DC drop, which we'll do later after part placement. It's important to get a decoupling strategy worked out early in the design process. We'll do this decoupling strategy in two steps. Right now, we're going to validate our proof of concepts to guide decoupling capacitor locations and values for pre-layout and determine a target impedance. And then later on, I will revisit this strategy once the board is more populated and do an advanced decoupling analysis to see if what I've recommended indeed passes all the checks for board sign-off and was the optimal strategy for our target impedance. I will use the decoupling wizard to automate this decoupling strategy so that I can find the best capacitor values, the total number of capacitors, and their locations. I will use the wizard to set a target impedance of 50 milliohms and sweep from 1 MHz to 100 MHz. I will use these settings again later on when I do the final decoupling analysis on the whole board. This is an iterative process, but the wizard makes it fast and easy to see the effects I'm studying and finding the best decoupling capacitors for this PCB. The first step that I've set up is an IC power pin and one decoupling capacitor with a 100 nanofarad value. And here is the plot that's received from that simulation. You can see that I'm well above my target impedance of 50 milliohms. What effect do we see when we move the decoupling capacitor further away from the IC power pin? We see that the overall inductance gets higher, our series resonance frequency shifts left and actually gets worse as the inductance gets bigger. The advice I would give to my layout designer is to put the capacitors as close to the IC power pin as possible. One thing that can have a great effect is to change the capacitor mounting scheme. Hyperlynx allows me to experiment with this as well by editing the capacitor that I am simulating. Hyperlynx allows me to model the capacitor mounting scheme and the mounting inductance and incorporate them into my simulation results. I can then run the analysis again and see some improvement, all at zero cost by changing the mounting scheme. The next thing to do is to add more capacitors to my what-if analysis. This will have an added cost, but it is necessary because I have not yet met my target impedance. After running the analysis again, we see a massive improvement, shifting the resonance down below the 50 milliohm target impedance. We can continue to optimize this by adding 5 more capacitors. By doing small chunks like this and using the wizard, I can do this a few times to find the best number where I can easily drop a capacitor or two to save some cost if necessary. 10 capacitors seems to be a good number here, so let's experiment now with the values of some of them to see if we can further optimize it. I set up a scheme of 5 capacitors with a 100 nanofarad value and 5 capacitors of 1 microfarad value, and place them near the IC power pin to run a final experiment. This seems to be the best setup for giving us plenty of margin to work with to meet our target impedance of 50 milliohms. Remember, this is pre-layout and a what-if analysis of one DDR4 DRAM with 10 capacitors. There will eventually be 4 DRAMs on this board, each with their own set of 10 capacitors that will also help to improve the performance. I will do a final decoupling analysis later on to make sure we still meet our target impedance when we start to populate the layout. My recommendations to my hardware and PCB teammates will be 5 capacitors of 1 microfarad and 5 of 100 nanofarads for each DRAM, as close to the IC power pin as possible, and with the capacitor mounting scheme that I've specified in this experiment. You can see the evolution of this what-if analysis. This upfront simulation work will give my teammates peace of mind knowing how many capacitors they have to work with when planning the layout placement, and saves precious time later on not having to rework critical areas of the board when designing the PCB.